Thank you, thank you. So open domain question answering, a classic challenge in artificial intelligence. Ever since artificial intelligence was even conceived of in the 50s, people thought, gee, how can I just stuff the computer with everything I ever know and then ask it some question and it's going to figure out the answer and solve my problem for me. And this has been the dream of AI, and it's been a long-standing expectation of course, of science fiction. And in fact, I have a couple of images up there. You have Star Trek. How many people like Star Trek, second generation? The computer in Star Trek was just amazing. I mean, I would just love to have one of those in my house. I could just dialogue with it and ask it anything. And what's interesting about it is that it didn't develop this personality or fall in love with me or anything like that. But what it did was it tried to understand my information need. It tried to understand my language. It summarized information and organized it for me. It gave me answers, and it even gave me probabilities around those answers. And that's a fantastic, fantastic capability, and you can imagine why we long for it, as human beings. Of course, the problem though is notoriously difficult in the general case, and part of what I want to talk about to you today is to get you to appreciate why that is really so difficult. I also have an image up there of a movie called Desk Set from 1957. It was remarkable. This was a movie where a media company invested in a big library and had a whole team of librarians, and they ended up hiring a scientist from IBM to come in and figure out how to build a question answering system to help the librarians so they could be more efficient. Back in 1957, really remarkable. Pick it up, it's a great movie. So why is question answering difficult? I mean, one of the interesting things that happened to me when IBM had announced the Jeopardy challenge, I got interviewed by a radio show host, and they said, okay, let me get this straight. So you have all these Jeopardy questions, you put them in like in a big spreadsheet, then you put all the answers in, and then when the question pops up, the computer reads out the answer, right? Does it read out the answer? I was like, no. I mean, we don't know what the question is going to be. We have no idea what the question is going to be ahead of time, never mind the answer. This is one, how do you do it? I said, exactly. That's exactly the challenge. So what is the expectation? There's this expectation that the way computers work for the most part are big giant databases or big giant spreadsheets where you kind of look stuff up in. But there's a big difference. The real difficulty comes from understanding the expression in the question and the expression in the content, and really mapping the meaning. So if I had a question like, where was X born? And I had this big database, these columns, right, with all the people in one column and all the places they were born in another, and I programmed the computer explicitly that every time it saw that question, it took whatever was in X and looked it up in the first column and pulled out what was ever in the second column. I put in Albert Einstein, and it would come out with Ohm, and it would be right. But I pre-programmed the computer to understand, to make the mapping of meaning from the question to the table precisely. What if I just gave it the string, the letters, where was X born, and it read a whole bunch of things? And among those things, it read, one day from among his city views of Ulm, Otto chose a watercolor to send to Albert Einstein as remembrance of Einstein's birthplace. The answer's in there, but how does the computer know the answer's in there? And there's a lot more work to do. It has to interpret the question with regard to what all the things it's reading. What's a birthplace have to do with being born? What are places? What are people? How do they interact? How do they connect to one another? How do they relate to the question? This becomes a much harder problem and starts to get you to appreciate how much humans are doing when they're interpreting the meaning in natural language. Here's another one. Jack Welch was the CEO of General Electric, and if I had pre-programmed the computer to say, well, every time you see a question that says X ran this, look up the X in the first column, answer what's in the second column, it's easy. But if I just give it, say, X ran this, it has no idea what it means. It reads a whole bunch of text. It sees if leadership is an art, then surely Jack Welch has proved himself a master painter during his tenure at GE. Maybe, at best, the computer might come back and say Jack Welch was a painter at GE, right? So there's a lot of complexity, in meaning. In fact, meaning is a really interesting thing. Meaning is not sort of encapsulated in the words and in the images we use to communicate with one another. In fact, those words and those images are really just pointers. They're pointers into our shared experience. We're both humans, we dialogue, we have shared experience, and we use language to orient ourselves within that experience. So it requires lots of interpretation that's ultimately grounded, not in the symbols themselves, but in what they represent in our shared experience. So here we have a picture of a calculator with some dice on top. Like to a computer, it's a bunch of zeros and ones that kind of represent the various pixels in that image. But when a human looks at this, they see the colors white, black, and red. They might see the objects, a calculator with dice on top. They may look at that and think calculating the odds. In fact, this image was labeled by a human as representing winning, the concept of winning. You could also think of it as representing the human use of tools. So there are many, many layers of interpretation in the simplest phrase or image. In fact, we could think of meaning as a probabilistic mapping from symbols to the shared common experience. And the richer the context, the more we can narrow the possibilities and zoom in on what that meaning, what is really intended by the symbol. So here I have the bat came flying toward the window. Lots of things kind of start lighting up in your head. You might think of a bat crashing through a physical window. You might think of a baseball bat or a cricket bat, and someone just swung it and it's flying toward the window. You might think of your ex-girlfriend taking a bat to your windshield. So lots of different things might be going on in your mind. So you need more context. The next thing you hear is Billy came running home. Still here, the intended meaning is ambiguous. You could think of if Billy was being chased by the bat and came running home. You could then think of, again, Billy sort of hitting the ball and running toward home base. Right? So you need more context to map those symbols to that experience. He made it home safe. You're still a little bit confused. He could have made it home safe and sort of is with his family now. He could have actually been called safe at home base. Finally, you hear he scored. And now you're pretty confident. You've assigned a lot of probability to the interpreted meaning that actually this was all originally about a baseball game or a bat came flying through someone's hand. So the more context you have, the more you can start to map those symbols to actual meaning, and that meaning is founded in that common experience. Why is it so important to get at meaning? Why isn't it enough just to find keywords in text? It's because the amount of information is growing incredibly rapidly, and we have more and more complexity in human life, and we have to get at that knowledge, and we have to get at it at a more precise and more concise way so that we can make better decisions. The healthcare bill is about 2,000 pages of natural language text. The 2006 tax code, 16,000 pages. The 2010, 71,000 pages. There's hundreds of thousands of medical textbooks and journals, and they're constantly changing as the knowledge is evolving. Print encyclopedia were 85,000 articles. Wikipedia now alone is 4 million articles. The internet provides access to the equivalent of roughly 5 billion books. What's in there that matters to me? And how do you summarize it? How do you understand it? How do you explain it? How do you pinpoint precise answers, precise solutions to the problems that I have? Jeopardy came along and it was a great challenge for AI because what it did is it set up a problem where you had a crisp metric, whether you won or lost this game against humans. And what was especially interesting about it was you couldn't solve it like this FAQ database. All the questions are here and all the answers are there. Because it was open domain, they asked about all kinds of things. There was complex language. If you're standing, it's the direction you should look to check out the wainscoting. In cell division, mitosis splits the nucleus, and cytokinesis splits this liquid cushioning the nucleus. Seems this perp was the first murderer in the Bible, and to top it off, he iced his own brother. Of the 4 countries in the world, the one the U.S. does not have diplomatic relations with, and it's the furthest north. Or, I'll tell you it was so cold today. How cold was it? It was so cold, I wish we were back in '64 when he was emperor. Hot times, if you know what I mean. So richly, complex language. What do the questions even mean? Never mind, how do I ultimately get at the answers? And to beat the best players, you have to have very, very high precision. But more than that, you have to have an accurate confidence, meaning that of all the documents and paragraphs that might come back if you did a search, where in there is the answer? And how confident am I that I actually have the correct answer? So you had to produce probabilities on your interpretation, your ability to map the meaning in the question to the meaning in the content you were analyzing, and you had to do this very, very quickly. Just to understand the question, this actor, Audrey's husband from 1954 to 1968, directed her as Rima the Bird Girl in Green Mansions. What's the question even asking for? It's actually asking for the director of the film Green Mansions, even though it says it's asking for an actor. Right? But if you know enough, this is really what it's asking for. But how do I even know that? If I knew that, then maybe I could map it to a database. This is actually a diagramming of the sentence the computer produces, and this is just the syntax of the sentence. What do all these things mean? What does direct mean? Like direct, guide, lead? What is Audrey, a person? What's Rima? A person, a girl, a character? What's Green Mansions? A place, a movie, a book, a house? How do I put all this stuff together and figure it out just to interpret the meaning of that? Again, humans use a tremendous amount of background knowledge and context to do all these calculations, and even then, it's probabilistic in nature, and they use more and more context to kind of figure it out. They use a lot of assumptions to figure it out. So here I have a simple question. In May 1898, Portugal celebrated the 400th anniversary of this explorer's arrival in India. Now, if I broke that sentence out and just looked at all the keywords, lots of things may come up if I did a search, but you can imagine, to make the point about evidence and about precision, imagine this paragraph. In May, Gary arrived in India after he celebrated his anniversary in Portugal. It has all the keywords in common. It's got arrived in, it's got May, it's got celebrated, it's got anniversary, it's got India. It says Gary is the explorer in question. Of course, it's not. It's Vasco da Gama, but who's to say, right? Well, we're all explorers in our own way. Imagine, imagine if it said, and then he returned home and explored his attic looking for a photo album. Right now, he's the subject of the verb to explore, which is reasonable evidence that Gary is, in fact, an explorer. Right? But humans use a lot of context and say, wait a second, I'm being asked about, is a country celebrating an anniversary? This has got to be one of the three explorers I remember from high school, probably not Gary. Right? So, same question, but we have a different passage now. On the 27th of May, 1498, Vasco da Gama landed in Caput Beach. This only mentions one keyword in common. There's got to be millions of passages that have the word May in them. Right? How would I know? I have to look far and wide. I have to look at lots of things, and how would I know this actually answers the question? So now I need different methods, lots of different methods that look at different things like geography, temporal reasoning, statistical paraphrasing. How do the words appear in the same context to suggest that they mean the same thing? Is this place contained in the other place? Are these things happening around the same time? Are they related in the right temporal relationship? So I build this evidence by many diverse methods, and I say, well, Vasco da Gama is probably a higher probability that that's the answer, at least more probable than Gary. So here now, if you have enough evidence, do I have 100% certainty? No, because I can make mistakes in all of these probabilistic calculations, because again, I'm not looking this up in a database that's intended to be complete or consistent. So language is messy, language is difficult. And one of the other really interesting challenges that came up in Jeopardy was this notion of a missing link. Here I have a question. On hearing the discovery of George Mallory's body, he's told reporters he still thinks he was first. There's like this missing piece of information in there that you need to connect the two parts of that query. So if I take George Mallory and I look at all the various things I know about George Mallory, one of them is he tried to climb Mount Everest, and then I can think, well, who was first at Mount Everest? And I can get the answer, Edmund Hillary. So the deeper that inference path is, the more complicated things get. But this allows the computer to answer more and more complex questions. And in fact, I'm going to close with a note on how the techniques that were developed in developing Watson for Jeopardy now can do things we never imagined could be done before in the medical space. How good did Watson have to be to beat grand champions? And this is a graph that shows the winner's cloud, all those dots in the center. And if you look at the middle of the dot, winning players were answering about 50% of the questions. They were doing about 85 to 95% precision. And that line at the bottom was the state-of-the-art question answering system when we started. And what you're reading there is if it had to answer about 5% of the questions, it did about 45% right. As it had to answer more and more, it plateaued at 17%, about 13%. That left an enormous gap to even getting anywhere near the winner's cloud and competing against humans at this task. We developed at IBM this architecture, this general systems architecture that would take a question, it would break it down into subparts, analyze it, it would do many searches. Again, Watson was completely self-contained, so it didn't have access to the internet, had its own library of things, which was another challenge, figuring out what that was. And then it would come up with hundreds of possible answers. And then for each one of those answers, it would fan out and get evidence, like passages and documents that might support that answer. So a huge fan out. And then for each one of those passages, it would run a diverse set of methods, various algorithms that the team of researchers would produce to judge that evidence, saying, does it have the right temporal information in it? Does it have the right geographical information in it? Does it have the right grammatical structure? Does it have the right kind of semantic relationships in it? And based on all these various algorithms, they would all contribute to a score and say, this evidence seems to support this answer to this degree. And you would ultimately have millions of scores because of all the different answers you would consider. They were all sort of like competing hypotheses and all the different passages. And then you combine all those scores and you have to weigh them. So Watson would train on previous questions and answers and figure out how to weigh all its own individual algorithms, how to balance them so that more often than not, it would get the right answer rather than the wrong answer, and it would have that final probability. And if that was higher than a threshold, it would want to buzz in and take a shot on that question. So computing that accurate confidence was, of course, very, very important. Over the 4 years, we had on average about 25 AI scientists and software engineers that I led. We had university relationships. We did 8,000 documented experiments. It was a huge engineering, science, and management effort, and we drove that curve all the way up to slicing across the winner's cloud, where if Watson buzzed in and got, let's say, somewhere between 60 and 70% of the questions it wanted, it would be answering in 85 to 90% precision, which was good enough to beat grand champions like Ken Jennings and Brad Rutter. Would it guarantee a win? No. In fact, we went into the game with roughly about a 70 to 74% chance of winning. So that means there was like, roughly a 30% chance of me losing my job. So the rest is history. We did win. The game was closer than you think. It was actually quite a challenge. The humans were remarkable. That answer panel at the bottom was an amazingly important communication because it got people to appreciate that this isn't about looking something up in a database. Watson's considering many possible answers and computing probabilities. And that was one of the most important things about this project. It changed the way people think about the role of computers. Rather than thinking of this precise, look it up in a table and it's never wrong, it's dealing with incomplete, inconsistent data and coming up with possibilities. And that's really the challenge of dealing with large volumes of data, which is complex, inconsistent, incomplete, and ambiguous. How do you cope with that? And if we can get computers to be our partners in coping with that information, we can make a lot of strides in dealing with the vast and leveraging the vast amounts of knowledge that is being created every day. From an AI perspective, it's fascinating. It was a challenge beating humans. Like I said, we were beating them, about 70% of the time. What humans got a brain, fits in a shoebox, powered by a tuna fish sandwich and a glass of milk, right? Gets a little hot, use a hand fan. The computer, 2,880 CPUs, cores, I should say, 2,880 cores, about 10 refrigerators in size, 80 kilowatts of electricity, 20 tons of air conditioning to compete against humans. And we still would lose questions, and we'd even lose to the buzz. In other words, the humans would beat the computer to the buzz because they were getting that answer so much more quickly than the computer was. Really, really fascinating comparison. So what was important about Watson? A triumph for general intelligence systems architectures. We set out not just to solve Jeopardy, but to build an architecture for dealing with this kind of information, for combining many, many different methods, for breaking down language and trying to understand it. It was a triumph for using a diversity of methods. We didn't go in there thinking, there's one formula that's going to solve question answering. Rather, there are going to be a lot of diverse methods that are going to be combined in a novel way. And it's reminiscent of a work by Marvin Minsky, one of the founders of AI, called Society of Mind, where I hypothesized that really intelligent systems have many, many methods that are competing and cooperating in different ways to actually interpret and understand things. The role of computers, as I mentioned, about really probabilistically dealing with incomplete and uncertain information. And finally, the role of computers in healthcare. And this is my last slide, which is, here's a United States medical licensing exam question. A 63-year-old patient is sent to the neurologist with a clinical picture of resting tremor that began 2 years ago, et cetera, et cetera, et cetera, and asks what part of his nervous system is most likely affected. What we did here is Watson broke that question down into different parts. And then for each of those parts, it would ask, we would call sort of the Watson many times. It would say, okay, what is 63-year-old associated with, or what might that cause, or what might that affect or be caused by? And we would do that for all the different pieces that were decomposed out of that question. And then for all the answers it would get, it would sort of repeatedly say, okay, now that I've got there, what does that cause? What might that be associated with? What might that be caused by? So it repeatedly called itself. And as it called itself, it propagated the confidences it got for each of those links. And the confidence is pooled at the right answer. So this is amazing because not a single if-then rule was written. Not a single knowledge base or database was created by a human. These are all non-experts who put together the system and then just used existing medical resources as they were written by humans for other humans. Nobody curated the data, nobody wrote if-then rules, nobody managed this big complex knowledge base. And this was actually on the verge of passing the United States medical licensing exam, at least part one of it. So that's just an amazing triumph for this type of AI, and for me, a culmination of really a 30-year journey in artificial intelligence. Thank you.